Okay, good morning, everyone, or good afternoon, or good evening, whenever you're watching this. So this is going to be a video about trigonometric functions for pre-calculus. And last time we talked about the unit circle, and that was really our introduction to trigonometry. Learning about the unit circle, learning about terminal points, and this idea of going around the unit circle counterclockwise for some distance. And we talked about a list of common terminal points and common t-values. T equals pi over 4, t equals pi over 3, things like that. You should know what terminal points those take you to. And then towards the end of that lesson, we talked about how to find other points on the unit circle besides that list of common terminal points. We can also look at other parts of the unit circle based on what we know from quadrant 1. All right, so let's start today with a little bit of a warm-up problem, okay? Let's switch over here. Okay, so this video is about trigonometric functions, but I want to start us with a warm-up problem covering some of the things from the previous lesson. So, example. Here, I'll write warm-up problem just so we have it in our notes. Warm-up problem, example. Find the terminal point determined by, I'm going to give you two of these. Part A, determined by t equals 5 pi over 3. And part B, we'll leave some space for part A. Part B is going to be t equals negative 3 pi over 4. So I'd like you to pause the video, take some time, and see if you can do both of these. Okay, for each one of these, I'm going to draw a scratch work unit circle. And I really hope that you are trying these problems when I ask you to pause, because the only way to get good at math is to practice problems yourself. I really think that you can't get good at math by just watching someone else do it. It's like learning how to ride a bike. You're not going to learn how to ride a bike just by watching someone do it. You need to try it yourself. You might have to struggle a little bit, but eventually everything will click. All right, I said we were going to have a scratch work unit circle. We'll be drawing a bunch of those today. You know, remember, those don't have to be perfect, but we're focused on part A right now. So where on the unit circle are we if we are at 5 pi over 3? So something that I did last time, and I'm going to do it again this time, is think of the unit circle as being chopped up into pieces. Like I know, for example, we always start at the usual starting point, right? I'll put a little dot there. And we know that if we go all the way around, we've gone 2 pi. I know that if I go halfway around the unit circle, that's a distance of pi. So how far around would a third of pi be? Going from here to here would be pi. I'll just mark that. That's pi. So if that's pi, a third of pi would look like I've gone a third of the distance to that. And 2/3 of pi would look like I've gone that much. So I'm taking the top half of the unit circle and chopping it up. I'll label this here. Pi over 3, 2 pi over 3. You see why I'm doing this? We're interested in 5 pi over 3. So I'm saying we go pi over 3, we go another pi over 3, another pi over 3. How about we go another one? How many have we gone at this point? 4 pi over 3. And then one more. This is when we've gone 5 pi over 3. Let's zoom in on this. So does that make sense? What if we went another third of pi? That would take us to 6 pi over 3, which would be 2 pi. So that makes sense. So sometimes writing little guides like this will help you. Let me get my blue pen out. All right, so we start at the usual spot. We go counterclockwise with a t-value of 5 pi over 3, and we stop here, and we want to know what is that terminal point, okay? So what reference number do you think we can use? Reference number. We talked about that in the previous lesson. I think the reference number that we could use, it's supposed to be the shortest distance along the unit circle between the terminal point we're interested in and the x-axis. So this right here that I'm pointing at, what distance is that? That is the reference number. And that looks like a distance of pi over 3. So I'm going to put that here. We know that pi over 3 has terminal point. What's this terminal point up here? This was on our list of common terminal points. It takes you to 1/2, comma, square root of 3 over 2. So 1/2, comma, square root of 3 over 2. So the answer that we are looking for, we want the terminal point for 5 pi over 3, and it's going to be some form of 1/2, comma, square root of 3 over 2. We just have to decide if there's a plus or a minus in front of each coordinate. I can tell that because we are in like the positive part of the, positive part of the x-axis, that the 1/2 is still going to be 1/2. But we are in the negative part of the y-axis down here, so we're going to have a negative y value. So it's negative square root of 3 over 2. That's my answer. So that's the general idea, is you maybe divide the unit circle up into some portions that make sense for what you're working with. I thought chopping it up into pi over 3, another pi over 3, to get 5 pi over 3s, I thought that made sense for this problem. The next problem looks like it has pi over 4, so I might do something different for that one. But you figure out where on the unit circle you are, you figure out what the reference number is, and then the terminal point for the reference number should be one of our common values, because it's in quadrant 1. And then your answer is going to look like what you already had. You just have to figure out if there's a plus or a minus. And in this case, there was a minus on one of the coordinates to get that to be down here, 1/2, comma, negative square root of 3 over 2. So I'm going to go through the next one a little bit quicker, but that's the general idea. Next one, I'm also going to draw a unit circle. Oh, this is a negative t value, right? So, again, I know that going all the way around is 2 pi, going halfway around the unit circle is pi. So, for example, if I had a t value of negative pi, I know that that would take me here. Negative pi would take me here. And we are going 3/4 of that, aren't we? 3/4 of the way to here. So, here's 1/4 of the way. Here's another 1/4 of the way. And now I've gone 3/4 of the way to pi. 3/4 of the way to negative pi. So this is where we're headed. I think the reference number. We've been talking about how this was a 1/4 of the way, a 1/4 of the way, a 1/4 of the way, a 1/4 of the way to pi. So the reference number that I've been really talking about is pi over 4. And that is this distance here, pi over 4. So pi over 4 is one of the common values on our unit circle, square root of 2 over 2, comma, square root of 2 over 2. So the answer that we want, we'll just go to the final answer now. It's going to be some form of the square root of 2 over 2, comma, square root of 2 over 2. We just have to figure out Are we doing pluses? Are we doing minuses? Look where the point is that we're interested in. It's over here. The x-coordinate would have to be negative to be all the way over here. The y-coordinate would have to be negative to be over here. So it's going to be negative square root of 2 over 2, comma, negative square root of 2 over 2. And that is the terminal point corresponding to t equals negative 3 pi over 4. So what we just did, we spent about 10 minutes doing a two-part warm-up problem. But the idea is that if you are given a t value, you should be able to find the terminal point. Now, within reason, I mean, there are certain t values that if I gave you them, we probably wouldn't know how to find the terminal point, but I'm going to be giving you ones that you can answer. I'm not trying to give you any trick questions here. They're going to be based on the common terminal points in one way or another. Now, this lesson is supposed to be about trigonometric functions, so how about we get started on that part? We're done with the warm-up problem. That was a good review of terminal points. There are 6 trigonometric functions that we want to talk about, but we're going to talk about them in pairs. So we're going to start by talking about 2 functions that are called sine and cosine. We're going to talk about them together because they're closely related. First of all, let t be any real number. And let x comma y be the terminal point. Determined by t. So you know that x comma y is on the unit circle, right? Because every terminal point is on the unit circle. We go some distance around, but we're on the unit circle, right? We define the following functions of t. I think that different t values take us to different x's and different y's, right? Like if I try t equals something and then t equals something else, right? So we get different x comma y's. We are going to define the sine function, which is abbreviated as sin. Sine of t is going to be defined. Are you ready for this? It's real simple. It's just y. That's sine of t. So sometimes it's written as sine parentheses t. It could be written either way. It's kind of like in math when you talk about logarithms and the parentheses are optional. Like if I said ln 5, or I could do ln parentheses 5, or I could just say ln 5. That's what's happening here. You could say sine t, or you could say sine parentheses t. And cosine of t is abbreviated COS. So that's cosine of t, and it is simply the x-coordinate of the terminal point. And this can also be written with parentheses around the t. Let's move this up. So this lesson is about trigonometric functions, and we just defined 2 of them, and they're actually pretty simple definitions if you understand what terminal points are. So, for example, scratch work unit circle. All right, example. We said that t equals 5 pi over 3 has terminal point 1/2, comma, negative square root of 3 over 2. That was the one we did earlier. That took us to about here. I just decided to use the warm-up problem that we did earlier. If we think of that as our x comma y, here maybe I'll write the t value on the t equals 5 pi over 3. I'm writing the t value on the kind of blue curve that I put on the outside, the blue arrow. So you go t equals 5 pi over 3. It takes you some distance around the unit circle. Eventually you stop at some terminal point. We know that this is what this terminal point is. We found it earlier. There's x, there's y. So in the context of these new definitions, this means that sine of 5 pi over 3 is equal to negative square root of 3 over 2. And cosine of 5 pi over 3 is equal to 1/2. So sine and cosine of a t value are simply the x and y coordinates, but you have to remember which is which. The y coordinate goes with sine, the x coordinate goes with cosine. If you can remember which is which, then anytime you find a terminal point, you're basically finding sine of something and cosine of something, because you found the y and you found the x. Here, let's do a quick problem. We'll do this one together. Maybe I'll start it and then I'll ask you to finish it. So given a t value, t equals pi over 2. I'm going to ask you to find part A. First, I'm going to ask you to find the terminal point determined by t. And next, I'm going to ask you to find sine of t, and next, cosine of t. But like I said, I'll start this out. I'll start this out for us. Let me just give you a chance in case you're writing that. So, part A we did last time. I want to say that we did part A last time, and you should have it in your notes. But I'm going to quickly remind you, we draw a unit circle, scratchwork unit circle. We always start at the same usual starting point. Going pi over 2 would go this far. That's how t equals pi over 2 looks. It takes us to here, and that takes me to the terminal point, 0, 1. We did it last time. We also said that's going to be one of the common terminal points that I believe was on our little table of common values. So let's put a box around that. That's the answer to part A. Part B. What is sine of t? Sine of t equals. For this problem, t is pi over 2. We found the terminal point, so sine of t is simply the y-coordinate, 1. And cosine of t, oh, you know what? I said I was going to have you try it. Why don't you just take a quick second? You don't have to pause the video or anything. Take a quick second and see if you can get part C. You should get that cosine of pi, cosine of pi over 2. You could call it cosine of t, or you could call it cosine of pi over 2. It's going to be 0. Just like over here, you could call it sine of t, or you could call it sine of pi over 2. Does that make sense? Wait, I wrote it on the bottom for the other one, so let's write it on the bottom for this one. All right, here's what I'm saying. What the problem asked us for, the answer is 1. We found sine of pi over 2 is 1, cosine of pi over 2 is 0. They're just the y-coordinate and x-coordinate from the terminal point. Now, sometimes you'll get a problem. If you're lucky, you'll get a problem like this that breaks it down into all these little steps. Find the terminal point, then find sine, then find cosine. But you could also be given a problem that just asks you to find sine or cosine of some number. So I'm going to going to ask you that. I'm going to ask you to find, without a calculator. We're doing all of this without a calculator, right? Because we understand how sine and cosine work. We understand terminal points. I'm going to ask you to find cosine of pi. So I'd like you to take a minute, pause the video if you need to, see what you can find for that. So I'll do a quick scratch work unit circle. How far around the unit circle is pi? We've been saying if you go all the way around, you've gone 2 pi. So going pi around the unit circle goes halfway around the unit circle. That's what t equals pi looks like. Means it takes me to here. It means t equals pi has the terminal point. We don't need a reference number or anything like that. We can figure this one out just from this picture. That is the terminal point, -1, 0. So cosine of pi equals, you just have to be careful. Which one is it? Is it -1 or is it 0? Well, up above, we had the definition for cosine. We said it is the x-coordinate of the terminal point. So cosine of pi is -1. And I kind of smeared the bottom of my y-axis. That's okay. Here, we'll get some white out on there. All right, so cosine of pi without a calculator, we found it is -1. How about one more of these before we move on to anything else? Find, without a calculator, let's say it's part A and part B. I'll ask you to find sine of pi over 3. And I'll ask you to find cosine of pi over 3. Let's take a minute, pause the video, see if you can calculate these. So really, these two problems, we can kind of solve both of them at once. So we draw a scratch work unit circle. And by the way, you could do this without a scratch work unit circle if you want. If you remember some common terminal points, you'll say, hey, I know that t equals pi over 3 takes me to this terminal point that was on a little table last time. So you might just know this point. This point was 1/2, square root of 3 over 2. So if you remember that point, if you see pi over 3 and you say, I know it takes me to 1/2, square root of 3 over 2, then you might be able to answer this problem without this picture. That would be okay with me. So we found that sine of pi over 3 is the y-coordinate of this, so it is square root of 3 over 2. And then part B, cosine of pi over 3 is going to be 1/2. So we answered both parts. See what I mean, where you kind of get both answers at the same time? It's just the two coordinates of the terminal point. Now we've seen in these little examples so far, we've seen that when you evaluate sine of something, or you evaluate cosine of something, you can get answers like 1/2, square root of 3 over 2, or you could also get an answer that's negative. We had one where the answer was -1. And we had one problem earlier that I'll just show you real quick, where we did one of them and the answer was 0. So the answer for sine or cosine of different numbers, it can be positive, it can be negative, it can be 0, it can be a fraction. Lots of different things it can be. We haven't really seen any of these where the answer is very large. We haven't gotten like sine of something equals 800. So maybe there's maybe if we start talking about like domain and range, maybe we could say that we'll say something about that soon. It seems like we get kind of small answers. But before we get to that, there are other trig functions I want to talk about. Now, I think I mentioned that there are 6 of them altogether. And we talked about the first 2 as a pair. We talked about the sine function and the cosine function together, because they really go together. The next trig function we talk about, I'm going to talk about just by itself. And it is the trig function known as tangent. Incidentally, just as a side note, I'll tell you, we're kind of going through these trig functions kind of in order of importance. I think sine and cosine are the most important, and then tangent is next up. So if x comma y is the terminal point determined by t, then tangent of t, which is abbreviated as tan t, or you could have parentheses, tan parentheses t, it is defined to be, well, it can't just be x and it can't just be y, because we already have sine and cosine that takes care of those cases, right? So it can't just be that simple. You know, it's not just going to be y, it's not just going to be x. It turns out we define this one to be y over x. So it's still a pretty simple little formula. And in fact, it's the ratio of one of the coordinates divided by the other. Now, how can you remember which one goes on top? Maybe you could say that there's one way to remember which one goes on top is it's a little bit like the formula for slope. When you do formula for slope, you have the y's on top, the x's on the bottom. I don't know if that helps or not. Let me tell you off to the side that this is defined whenever x is not equal to 0, because this now has a denominator, so that denominator could be 0, and in that case, tangent of t would be undefined. So for sine and cosine, we always got answers, like maybe it was positive answer, maybe it was a negative answer. For tangent, it is possible to get a problem that has no solution, because you might be dividing by 0. Let's see. Let's do a problem. All right, example. Find the terminal point. Determined by t equals pi over 6, and use your answer to find tangent of pi over 6. I'd like you to try this one without a calculator, and probably you want to pause the video and take a couple of minutes and work on this one. Okay, so hopefully you spent a little time working on this and you've gotten to an answer. I'm going to say pi over 6 is a pretty small t-value. That only goes a short distance. I mean, if you wanted to accurately get like the picture to scale, you could take the top half of the unit circle, chop it up into 6 equally sized pieces, and say that this goes one of them. Maybe I'll do that just to show you what I'm talking about. The top half of the unit circle chopped into 6 equally sized slices. You're slicing up a piece of pie or something. Top half, why did I say the top half? Because the top half would go all the way to pi. We are going 1/6 of that. So this was one of the common terminal points in I should just say in the previous lesson. There is a textbook that I'm referencing, but mostly in these videos I'm not using section numbers. I'll just say in the previous lesson. Just in case by the time you watch this video, there's like a different edition or something. Anyway, in the previous lesson, it's in the previous section of the textbook that I'm referencing, we said that t equals pi over 6 has terminal point square root of 3 over 2, comma, 1/2. It was on the list of common points to know. So, what does that mean for tangent? Tangent of pi over 6 is supposed to be y over x. So let's take the y and put it over the x. Is that the answer? Sort of. That is the answer, but I would like to simplify it. I don't like having a fraction on top of a fraction. I don't think we need to leave it like that. We could simplify. There's a couple of different ways you could think of to simplify this. One thing is I have 1/2 over square root of 3 over 2. I could say that, what if I multiplied this by 2 over 2? We're allowed to do that. Multiply by 2 over 2. That would simplify it to this. Or if you didn't think of that step, if you didn't think of multiplying by 2 over 2, another way to handle it is you could say, instead of dividing by a fraction, I'm going to multiply by the reciprocal. So yeah, take what's on the bottom. Instead of dividing by that, multiply it by the reciprocal. You would also get to here. That would take you to here. There's one more thing that I would like to do, though, because generally in classes like this, we don't like to leave square roots on the bottom. We like to do something that's called rationalizing the denominator. Basically, getting square roots out of the denominator. And a way that you can do that is multiply this by square root of 3 over 3. Square root of 3 over square root of 3. You're multiplying, again, by itself. You know, so like here, 2 divided by itself is what I did. Over here, square root of 3 divided by itself. That kind of simplifying step helps with fractions. Here, it's going to give me the square root of 3 on top and a 3 on the bottom. And we prefer that answer compared to the previous step. We prefer this because now the square root is on top instead of on the bottom. So I'm going to put a box around this. And we found that tangent of pi over 6 is equal to the square root of 3 over 3. So it's a little bit more work than sine or cosine, you know, because of the simplifying that had to be done and working with fractions and square roots and stuff. But it's not so bad. Just remember that tangent is y over x. So really, if you find the terminal point of a t-value, you can very quickly get sine and cosine, and you can then do maybe like one or two steps and you'd find tangent. So you can find sine, cosine, and tangent if I give you a t value. Now, I said that there were going to be 6 trig functions. We've talked about 3 of them. We're going to talk about the other 3 altogether. The other 3 trig functions are cosecant, secant, and cotangent. And I've decided to list those in this order for a specific reason. So, how did we start the definitions for sine and cosine and tangent? We started them by saying, if x comma y is the terminal point determined by t, then. Okay, I want to give definitions for all 3 of these things. They are also going to be abbreviated with 3 letters each. Like sine was S-I-N, tangent was T-A-N. All right, cosecant, secant, and cotangent of t. So cosecant is abbreviated like this. Secant of t is abbreviated like this. And cotangent of t is abbreviated like this. And again, if you want, you can put parentheses around the t. That's optional. So, what do these equal? I didn't actually fill it in yet. We're going to have a little formula for each of them. We don't need a lot of space. They're pretty simple formulas. The formula for sine and cosine and tangent, those were all based on x and y. So cosecant is going to be 1 over y. Secant is going to be 1 over x. That's not so bad, right? That means that if you find x comma y, you just put 1 on top of it, right? Or maybe you might have some other simplifying to do to make the answer look nicer so that you don't have a fraction in a fraction. You know, you might have a little simplifying step to do. But if you find x comma y, you can find cosecant and you can find secant. Cotangent is x over y, which kind of looks like a flipped upside down version of tangent. And it is called cotangent. It's the reciprocal of tangent. Now, each of these, I should say, does have kind of a restriction. This is defined when y is not 0. This is defined when x is not 0. This is defined whenever y is not 0. So, you know, these could be undefined. If I gave you a certain t value, if you're dividing by 0, you just say it's undefined. So we've defined all 6 trig functions. They're all based on terminal points. They're based on x and y from terminal points. Now, I'll just say that if you've seen trig before, if you've seen trig functions before, like sine and cosine and tangent and these other ones, there are also other ways to define these trig functions, which we're going to get to later in the course. There are some ways to define these that are based on triangles instead of circles. Okay? But ultimately, where we're headed in this course is we're going to see that both perspectives on trig functions are equivalent to each other. They are simply just different perspectives on the same thing. And the sine, cosine, tangent, and these 3 that we're talking about, it's the same sine, cosine, and tangent. And these, it's the same as the triangle version. Okay? We're just doing it based on circles right now. I said something a minute ago out loud that kind of stood out. I said cotangent of t looked like the reciprocal of tangent. Because, you know, earlier, you know, maybe on the previous page, we said tangent of t is y over x. cotangent of t is x over y. It's the flipped version. So we have what we call reciprocal relations. And they are basically just some facts. So sine of t is y, and cosecant of t is 1 over y. So they are the reciprocal of each other. We could say cosecant of t is 1 over sine t. And we call that a reciprocal relation. Cosine of t is x, and secant of t is 1 over x. So secant of t is 1 over cosine of t. That's another reciprocal relation. I'll say cotangent of t is x over y. So cotangent of t is 1 over tangent of t. So you see what happened here is earlier we talked about sine, cosine, tangent. And I saved these three to talk about last, cosecant, secant, cotangent, because these three are just the reciprocal of the first three that we talked about. You do have to remember which one matches up with which one. I think it's easy to remember that tangent and cotangent go together, because they both have tangent in the name. But then it might be a little confusing to remember, like, which one of these goes with which. So looking at these reciprocal relations, I think a way you can remember it, I don't know if this helps or not, but cosecant starts with a C, but it actually goes with sine that starts with an S. Secant starts with an S, but it actually goes with cosine, which starts with a C. So you might remember that these ones are a little backwards if you're trying to go by the alphabet. They don't match up letter to letter. I don't know if that helps you remember it or not, but you could just remember that we defined cosecant to be 1 over y, we defined secant to be 1 over x, and it follows from there. I've got one more thing here under this heading of reciprocal relations also. This is something we could have actually said earlier, but we didn't say it till now. Tangent of t is y over x, so that means tangent of t is sine of t over cosine of t. That's pretty cool. That means that these three, the first three trig functions that we talked about are related to each other in this way. So we've just defined a lot of things. I want to give you a problem to try. I think now if I gave you a t value, I could ask you to find all 6 of the trig functions evaluated at that t value. And that's what I'm going to do. So again, without a calculator, I want you to find sine of 3 pi over 2, cosine 3 pi over 2, tangent of 3 pi over 2, cosecant of 3 pi over 2. I'm making it easy by making it all the same t value. Secant of 3 pi over 2, and cotangent of 3 pi over 2. Hint, before you do this. Hint, some of these are undefined. All right, so now you could take a minute. I would draw a unit circle for scratch work. Take a minute and see if you can do these. All right, so hopefully you tried that and you're checking back with me now. Let's figure out what part of the unit circle we're on so that we could figure out the terminal point, because I think we're going to need the x and y coordinates. I think we might have labeled 3 pi over 2 on the unit circle we did at the end of the video last time. Anyway, so if I went pi over 2, here, if I went pi over 2, it would be here. So if I went another pi over 2 to take us to pi, it would be here. And then if I go another pi over 2, it would take me here, and that would be 3 pi over 2. So it's taking us to this part of the unit circle. Makes sense, because remember, if you go all the way around, it would be 2 pi. This part of the unit circle has terminal point 0, comma, -1. So how about I just point to this? This is x, and this is y. So now I think we could find all 6 of these trig functions evaluated at 3 pi over 2. Some of them will be, some of them will be really fast. Sine of 3 pi over 2 is simply just the y coordinate. Cosine of 3 pi over 2 is simply the x coordinate. Tangent of 3 pi over 2 is y over x. Y over x. Y over x. That is undefined because we're dividing by 0. Over here, let's do the other 3. Cosecant 3 pi over 2. Cosecant, well, we could know that it's the reciprocal of -1, but basically it's 1 over -1, which is -1. Let's do secant of 3 pi over 2. Wait a second, is this going to be the reciprocal of 0? The reciprocal of 0, or 1 over 0, is undefined. So I did tell you that some of these were going to be undefined. Cotangent, 3 pi over 2. Hold on a second. Let's think about this. We said tangent was undefined. Does this mean that cotangent is also going to be undefined? Because it's 1 over undefined, like the reciprocal of undefined? Like 1 over undefined? Well, no, we can actually say that cotangent of t is x over y. So it's the reciprocal of these, -1 over 0, like flip that. 0 over -1. That is defined. 0 divided by -1 is defined. It equals 0. When you do 0 divided by a number, you get 0. So we answered all 6. Without a calculator, we know how to do sine, cosine, tangent, cosecant, secant, and cotangent of this t value. And I could give you a problem like this with a different t value. And it's a good way to give you kind of 6 problems in one. All right, so a little bit earlier, I think I may have said something out loud about the domain. So, you know in math classes that anytime we introduce a new kind of function, there are a few things we like to talk about. We like to talk about the domain, the range. We like to talk about the graphs of functions. And for now, let's at least talk about the domains. So we're going to group these together, the function and what the domain is. Because it turns out there's kind of a pattern. if you look at the function sine or the function cosine, the domain winds up being all real numbers. What that means is you can put in any value of t that you want. T is the variable that we're putting in. You can put in any t value. T could be positive, t could be negative, t could be 0, t could be 1,000,000. I guess if t is 1,000,000, it means that you went around the unit circle a bunch of times, right? Eventually you stop somewhere. So all real numbers are okay. For the other trig functions, we have to say the domain is something different, though, because remember, the other trig functions have denominators, and we don't want the denominators to be 0. That's when you get undefined. For example, for tangent, I think I should say 3 pi over 2 is not in the domain of tangent. It's an input that if I try to put this input into this function, it's undefined. So 3 pi over 2 is not in the domain of tangent. 3 pi over 2 is not in the domain of secant. There's going to be some stuff that's not in the domain of the other ones also. So I'll tell you what the pattern is. Cotangent and cosecant. They've been defined so far in the examples we've done, but we said that for cotangent and cosecant, we want y to not be 0. Well, when would y be 0? Y would be 0 if we are at this part of the unit circle. Y would be 0. Or this part of the unit circle. Y would be 0. So we state the domain to be the set of all t values such that t is not equal to a multiple of pi for any integer n. What this does is stating the domain in this way says it can be any value of t except for pi, 2 pi, 3 pi, 4 pi, 5 pi, negative pi, negative 2 pi, negative 3 pi. 0 can't be any multiple of pi because we would be dividing by 0. For the other two, tangent and secant, there's also a pattern. It's going to be t such that we already said 3 pi over 2 looks like a problem. I mean, you can see what part of the unit circle we're on. The reason why this was a problem is because x is 0. We were dividing by x. We were dividing by 0. There's another part on the unit circle up at the top where x is also 0. So there's 2 problem points here. They're a distance of pi away from each other. So what we say is t is not equal to pi over 2 plus n pi for any integer n. This means tangent, secant, it means that they are defined for most values of t, all values of t, except for these values. And this would be pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Like all of those places that take you to these terminal points where x is 0. Those are not in the domain, but everything else is in the domain. Okay. It does mean that sine and cosine are kind of nice, that sine and cosine are defined for all real numbers. I mean, this is pre-calculus, and I'll just tell you that having a domain of all real numbers is pretty convenient for calculus. Also, sine and cosine are going to wind up being used for some real-life applications, and it's nice to know that we don't have to really think about the domain too much when it's just sine or cosine. Okay, now we've got a little bit more. I've got a question. I'll talk about this question. You've answered some problems already today. I'll talk through this one. What are sine of negative t, cosine of negative t, and tangent of negative t. So suppose we draw a unit circle. I basically want to see if there's like a little pattern or a formula for these. Let's say we go some distance. We'll keep it kind of vague because we want to be general here, but let's say we go like some distance t, like this, and it takes us to some terminal point x comma y. Can we figure out what would happen for negative t? Here's what I'm going to do. If what I just drew is t, then negative t would go the same distance, but in the opposite direction. So negative t looks like this. And that would take me to a terminal point down here. What I'd like you to see is if I drew this just perfectly to scale, and like if everything lines up the way it should, I'm hoping that you notice that the 2 points are directly, one is directly on top of the other. Like, I'll draw a little dotted line. You know, this is the x coordinate. They should have the same x coordinate. This is x comma something, because one is directly on top of the other, same x value. What about y? Well, because the circle is perfectly symmetrical, and this is like the top half of the circle is like a mirror image of the bottom half of the circle, this should be negative y. So when we go negative t around the unit circle, it should have this effect of flipping the y coordinate. So now let's see if we can answer these 3 questions. Sine of negative t, it would be the y coordinate of this terminal point down here, which is negative y. So do we just say that's the answer? Yeah, that kind of is the answer. But I want to show you something else. Not only could we say it's negative y, but we could say that it is negative sine of t. Check that out. And that might be something that's useful to know as a general rule, that sine of negative t is equal to negative sine of positive t. Do you think the same thing happens for cosine? Cosine of negative t? I mean, sine and cosine are so similar. Sometimes they, we might think that the same thing is going to happen. However, look at this. Cosine of negative t is just x. And x is cosine of t. So we're not getting the exact same pattern here, the exact same behavior. This time, cosine of a negative t is the same as cosine of positive t. We saw that in our picture. Because what we just said, that when we go use the negative to go in the opposite direction, we still get the same x value. Finally, what is tangent of negative t? Well, we'll do the reciprocal, right? We could do, actually, let's use this reciprocal relation. Let's use the sine over cosine rule. There's a negative in there. Remember we said tangent of something is sine of it over cosine of it? So sine of negative t is negative y. Cosine of negative t is x. So we get this. So what we wind up with is negative tangent of t. So each one of these things could be used as a fact. We could remember this as kind of some facts about sine and cosine and tangent. Is that the sine of a negative t is the same as negative sine of t. Cosine of negative t is positive cosine of positive t. And then tangent of negative t is negative tangent t. What we're doing is we're starting to establish some facts about these trig functions. facts, or you might say properties. I'll show you another one. Recall the unit circle equation. X squared plus y squared equals 1. Okay, that was in the previous lesson. Now, we said today that sine of t equals y and cosine of t equals x. So what we're going to do is we're going to put these together. The unit circle equation and the two little definitions we said today for sine and cosine. What would the unit circle equation look like if we replace x with cosine and if we replace y with sine? It's going to look like this. Sine of t squared plus cosine of t squared is equal to 1. Okay, so that by itself, that's kind of another fact about how sine and cosine are related to each other. The function sine and the function cosine. And this seems like this is true for any value of t. We said the domain of sine and cosine was any real number. So yeah, any value of t. This is true. And this is usually rewritten as, there's a different notation here. Usually instead of sine of t in parentheses squared, we write it as sine squared of t plus cosine squared of t equals 1. For any, I'll say for any real number t. This notation might seem a little weird. It's weird where we're putting the squared. Sine is getting squared. But it's understood that what we just wrote means what we had on the previous line. So this is an interesting fact about how sine and cosine are related to each other. It's true for any real number t. And this fact is an example of what we call a trigonometric identity. A trigonometric identity, that's something that we're going to talk about more later in the course. But for now, we can still talk about some of them. There are going to be a lot of trig identities. And they are basically going to be facts about how these trig functions relate to each other. This is one of the ways that they are related. Sine and cosine are related in that for any real number, you get this. For example, if I asked you, what's sine squared of 7 plus cosine squared of 7? I don't even know what sine of 7 is. It would be some weird decimal or some weird fraction, right? Or some weird thing with square roots. We don't know what sine of 7 is, but it doesn't matter. According to the trig identity, this thing must add up to 1. If I said, what's sine squared of pi over 4 plus cosine squared, let's put some parentheses here, of pi over 4. Now, I do know what sine of pi over 4 is. So we could figure out what sine of pi over 4 is and then square it. We could figure out what cosine of pi over 4 is and then square it. According to this trig identity, it's guaranteed that that's going to add up to 1. I'll just say etc. You could put in 0. This says any real number t. You could put in 0. This would still be true. Okay. a couple of other trig identities for now. Like I said, we'll talk about more later in the course, but it's good to start thinking about some of them now. If we start with the one that we had above, and we divide both sides by cosine squared t. So sine squared t over cosine squared t plus cosine squared t over cosine squared t equals 1 over cosine squared t. Let's simplify this a little bit. What we're trying to do is start with a trig identity, do some kind of step to it, and it's going to give us some new trig identity after we simplify it. So this simplifies to sine t over cosine t squared. This simplifies to 1. And this I could write as 1 over cosine t parentheses squared. Do we want to say that this is another trig identity? Technically it is. I mean, this is a it's an equation about how sine and cosine are related to each other. It has an equal sign. But there's another nicer way to write this. Sine of t over cosine of t is also known as tangent. So this is saying tangent squared of t plus 1 equals 1 over cosine is better known as secant. So check this out. We got a new trig identity. And this one is telling us about how tangent and secant are related to each other. Pretty cool. We started with the first trig identity we had came from the unit circle equation. And now we kind of did some step to this, and then we were able to get a new trig identity. So this tells us tangent and secant are related to each other in this way. Here, I'm going to kind of section this off a little bit. I want to show you something else. What if we took this, and instead of dividing both sides by cosine squared, you could say, why did I divide both sides by cosine squared? Well, I guess I did because I knew it was going to work out and give us something. What happens if you divide both sides by sine squared t? Let's see what happens if you do that. So you get sine squared t over sine squared t plus cosine squared t over sine squared t. This is going to wind up getting us a different trig identity after we simplify it. This thing simplifies to 1. This simplifies to, let's see, cosine t. We'll do another simplifying step after this, but we get that. We'll do one more final simplifying step. The 1 is going to stay 1. Cosine of t over sine of t is cotangent. So this is cotangent squared of t, and 1 over sine is cosecant. So 1 over sine. So look at this. This is an entirely new trig identity for us. And now this one tells us how these two trig identities are related to each other. They are almost equal to each other. They're just off by 1. Right? One of them is 1 greater than the other. Well, I guess we should say as long as they are being squared. To be clear, this is not about cosecant and cotangent. This is about cosecant squared and cotangent squared. And those two things are only 1 off from each other. Before I move on from this, I want to put a box around something else here. This is the trig identity that we were using, that this stuff was based on. I want to put a box around it just so that we can look at this page and say, these are 3 trig identities that are all kind of similar to each other. These are facts about how trig functions are related to each other. All right, let's do a little more before we stop, because I've got some extra little practice problems that I think we should do. Maybe I'll do some of them and have you do some of them. What have I got here? So let's find some more of these trig values without a calculator. So I'll do part A, and it will be tangent of 2 pi over 3. I don't think we did that one yet today. I'll do that. And then I'll ask you to try we'll leave some space. I'll ask you to try B is going to be cosecant of negative 5 pi over 6. And I don't know if I have any more. After this, we'll see if I have any more. So I'll do part A. So here's what I'm going to do. I'm going to say, I know that tangent of 2 pi over 3, I could think of it as sine of 2 pi over 3 over cosine of 2 pi over 3. That might help me. Let's do a unit circle. Do this over here. Let's figure out where we are so that we could figure out the terminal point. 2/3 of pi. So pi is here, and I want to start at the usual starting point, and I want to go 2/3 of the way to pi. This would be 1/3 of the way. This would be 2/3 of the way. Can you see that? 2/3 of pi goes 2/3 of the way to pi. Do we know this point on the unit circle? It's not one of the common values from that little table that we had last time. It's something that maybe we could figure out by doing a reference number and then, kind of referencing something in quadrant 1. Here's what I'm going to say, though. I think I can kind of tell from this picture. If I know some common values, go ahead and do a little more work for the reference number if you need to. But if you can tell, it's okay to say this is negative 1/2, comma, square root of 3 over 2. I can kind of tell because it looks like this point that's in quadrant 1, except I know that the x-coordinate has to be negative because we're in quadrant 2. Let's get back to the problem. The sine of it, I guess, is the y value. So that's square root of 3 over 2. And the cosine of it is the negative 1/2. So technically that is the answer, but it looks really messy, and I would like to simplify my answer. When I have a fraction over a fraction like this, if they're both the same denominator, my thought is usually, let's multiply the 2 over 2. It's going to cancel all these 2's. I'm going to be left with square root of 3 over negative 1. And my final answer is negative square root of 3. So I'd like you to take a minute and try part B. Pause the video, give it a try, and then check back with me. Cosecant. So cosecant, we could say, is 1 over sine. So you could start off thinking of it this way. Does that really help us? I guess now we've kind of turned it into a question of what is sine of that t value. So I'll draw a little unit circle to help me figure that out. I feel like we might have done negative 5 pi over 6 last time as one of those terminal point examples. I don't remember like 100% for sure if we did that one, but it seems familiar. That's going to take us here on the unit circle. It's negative, so we get there by going clockwise. And we go 5/6 of the way to pi. So almost all the way to pi, which is meaning almost halfway around the unit circle. And again, you could figure this out based on a reference number. Your reference number would be pi over 6. You'd figure out the terminal point for pi over 6, and then you would figure out if you need pluses or minuses. So this winds up being negative square root of 3 over 2, comma, negative 1/2. That's the terminal point. From the terminal point, I can find the sine is negative 1/2. That's really all we needed. We didn't even need the x coordinate. Only really needed the y value. 1 over negative 1/2. Let's simplify that. That simplifies to negative 2. Why don't we do one more? I do have one more. I don't think we did this earlier. I'm going to ask you to try to find tangent of 3 pi over 4. Or you know what? I'll say it's up to you. If you want to try this on your own, you can pause the video. Or it's okay if you just want to watch me do this one. Okay? So I'm going to do this problem here. Tangent of 3 pi over 4. I'm thinking of this as sine of 3 pi over 4 over cosine of 3 pi over 4. Does that help us? Well, maybe. It takes one problem. It breaks it up into two smaller problems, maybe. Let's draw a unit circle. Let's figure out where are we on the unit circle if we have t equals 3 pi over 4. That's 3/4 of the way to pi. So here's my starting point. I've gone around 0. Here's where pi would be if we went t equals pi. We want to go 3/4 of the way to that. So here's 1/4 of the way. Here's another 1/4 of the way. And here's another 1/4 of the way for a total of 3/4 of pi. 3/4 of pi. I recognize where this is on the unit circle because I know that this point here, maybe I'll zoom in on this. You see, this point here I know is an easy one, is root 2 over 2, root 2 over 2. So that means, you know, this corresponds to just pi over 4. If we just went pi over 4, we'd be at that point. That's my reference number, by the way, for this problem, where I want to say that the x-coordinate now is negative. The y-coordinate is still positive, because look at where we are. We're in quadrant 2. That's a positive y value, but a negative x value. This is going to get used as my x and my y, also known as my cosine and my sine. I'll give you just a chance if you're writing any of that down. All right, let's get back to the actual problem. So sine of 3 pi over 4, we found that that is the square root of 2 over 2. Cosine of it, we found, is negative square root of 2 over 2. So what have we got here? A fraction over a fraction. It looks like a mess. We'd like to clean it up. I'm thinking, do you want to do, like, should we multiply by 2 over 2? We could do that. Or we could flip things around and say, instead of dividing by a fraction, I'm going to multiply it by the reciprocal. You could do that. I see a quicker way for this simplifying. We have a number divided by itself with a minus sign. That means this must simplify to -1. Because it's a number divided by itself. So it equals 1. And the minus sign is still there. Okay, so we'll be finishing up in just a moment. I'll just leave this for a second here if anyone is writing that down. Notice it's just a coincidence that all 3 problems on this page, the answers were negative. I don't know why it worked out that way. But we've seen today that when you evaluate trig functions, sometimes you get an answer that's negative, sometimes you get an answer that's positive, sometimes it's undefined, and sometimes you could get an answer that's 0. Okay, so that was our lesson on trig functions. Really, this lesson could have been called an intro to trig functions because we're going to be doing more with them in the upcoming lessons. So we're not finished with them, not by any stretch. We're going to see these trig functions all semester. So let me just give you an idea of what's coming next. So I mentioned in the middle of this lesson that anytime we are in a math class where we introduce a new type of function, there are a few things that we like to look at: domain, range, and graphs. They're just kind of useful things to know about a function. So the next lesson is going to talk about the graphs of these trig functions, which you might say, we drew a lot of pictures today. Are those the graphs of sine and cosine and tangent? Those are not really the graphs. Those were just unit circles. The graph of the function sine and the graph of the function cosine and etc. We're going to talk about those next time. Okay? And maybe as we do it, we'll talk about the range a little bit. So that's where we're headed. All right, so take care, everyone, and I'll see you next time for the trig graphs.